all able to see the homework? Just posted. Anybody have any questions about that? I'll tell you, the waveguide stuff, because I'm going to go through something in a second that'll make it a little more real. Now, I posted some additional notes. Did y'all see them? All right. I want to go through a bit of that before I get into the fiber optic stuff, and because this is how a waveguide can be used like a transmission line. And I think it's shown there. You tell me if it is or not. Unless, does anybody have any question about that? Because this is a problem that will be more sensible to you. So suppose we have a waveguide. I'm just going to draw the cross section of this guy here. This is a waveguide. And we're going to assume it has a certain length L. And without getting into it, when you attach to a waveguide, you basically have a horn that usually is attached to the end of it. Right? So you're going to radiate power, and if you're going to just take that power and conduct it into some other region, you can. But waveguides are used to conduct power almost always that ultimately ends up on an antenna. So this would be like a horn antenna. And we'll get to antennas in a second. This would be a horn. Now, I'm going to assume that this horn antenna is really a load, can be represented like a load. Now, so I'm going to do this. I'm going to erase it. Remember, it's a horn antenna, and I'm just going to put ZL here. And this represents a horn antenna. Okay. Now, this has a characteristic impedance Z0, but it has to do with the guide's mode. And we're going to say this is going to be a TE10 mode on here, okay? This is important that you see this. Now, it's attached to a generator, and the generator, without getting into the details too deeply, there's going to be some RS of the generator, then here's the generator, plus or minus V generator. And what we're going to do is analyze this like we would a transmission line problem, okay? So the first thing is, we have to calculate this characteristic impedance. You follow me? So that means there has to be an operation frequency. I'll call it F. And F has to be greater than FC10. It has to be greater than that. Now that means the dimension of the guide, the A dimension, the Y dimension. And I'll put down A, let's do it this way. A before was 2.5 centimeters. Do you remember this one from last time? 2.5 centimeters. Let's assume the guide is air-filled. All right. Now, we have to calculate FC10 for that mode. Do you remember how to do it? What did I say that this was? What would the cutoff? If that's A, what does that represent? That's the wide part of the guide, right? The cross-sectional. And what was that at cutoff, class?
6 gigs.
Well, it's wavelength over 2, wasn't it, class? Isn't that the wavelength over 2, lambda over 2 equals A? Y'all, how many remember that? Right? So at cutoff, A is equal to lambda, right, divided by 2. By the way, that's free space lambda, so I'll call it lambda naught. Lambda naught in the book always represents free space lambda. And that means A times 2 was lambda naught, and lambda naught is C over F for an air-filled guide. And that means F cutoff, 1O, would be equal to C over 2A. C is 3 times 10 to the 8th meters per second, right? And 2 times 2.5 times 10 to the minus 2, so that's 3/5 or 0.6. Is that 6 gigahertz?
Yes, sir.
So 6 gigahertz is the cutoff. And the FC20 mode is actually 12 gigahertz. Y'all remember that's twice the 20, because the A dimension, right, is more than twice as big as the height. The next cutoff will be the 20 mode. You follow me, class? And that's 12 gigs. So I'm going to operate between these two. My operation frequency is going to be F equals 10 gigahertz. All right. Now at 10 gigahertz, if we're gonna do this, what I'm really after is this. I'm after the voltage here, voltage at the low. That's what I'm after. And also the reflection coefficient. Reflection coefficient at the low. So if I'm at 10 gigahertz, and I'm in a 1 ohm mode, and it's TE, do you remember the characteristic impedance, ZTE 10 was the characteristic impedance of free space, or A to naught, 120 pi, and it's divided by the square root of 1 minus, and this would be the cutoff frequency, which would be 6 gigahertz, 6 gigahertz, divided by the operational frequency, which is 10, so it's going to be 0.6 squared, right? And we did this last time, so that's 120 pi divided by the square root of 0.6 squared is 0.36, 1 minus 0.36. What does that come down to? Is it 470? It was 377 by.
Yeah, it's 471 ohms.
471 ohms. All right. Now, we can get the reflection coefficient, and that would be ZL minus that, really minus, call it Z0 TE, or Z0 TE10 over ZL plus Z0 TE10, and I'm gonna, for the heck of it, I'm gonna say that ZL here is 400 ohms. So say the antenna has a 400 ohm impedance. So what is that reflection coefficient? It's not quite matched. The driving point impedance is 471, I'm at 400. What do you get for reflection coefficient? It's negative something. 0.2, is it? 0.1? I'm trying to give you a real life problem. We would like to have the driving point impedance be equal to 400 ohms, right? I mean, we'd like to have either the antenna be 471 or the waveguide be 400. You follow me on this, class? Remember that impedance of the guide is what you're actually feeling at the antenna, right? That ZTE10. Are you with me, class? Give me this. So you got ZL 400 minus 470, right? Is minus 70 over what? 870, right? What is that?
Negative 0.08.
Right. Minus 0.08, all right, is the reflection coefficient, which is not too bad, right? And what's the standing wave ratio then? Voltage standing wave ratio. Do you remember how to get that?
1.
It's actually, remember this, it's 1 plus the magnitude of the reflection coefficient over 1 minus the magnitude of the reflection coefficient at the load. So what is that? It's 1.08 over 0.92, right? What do you get for that? Did you have a test there or something?
1.17.
Anybody else?
Yeah.
All right, that's not bad. That's acceptable. It's not perfect, but it's not bad. Follow me? If it was 2, if it was 4, yeah. All right, but about 1.17 is more or less, that's okay, not too bad. And we probably would have tuners in the real world. So now I have that. Now the next thing I'm going to do is say this. I'm going to say L is going to be equal to, say, 8 centimeters. All right? Are you with me? Now, how do I calculate the impedance right here that I'm seeing? I would like to know what Z in is here. Can everybody appreciate this? This is just like the transmission line problems, right? Now let me show you something. Remember, Z in on a transmission line was equal to the characteristic transmission line impedance, but I'm going to put Z0, now it's going to be TE10 here. Then it's going to be times Z load, right, plus J, this is for losses, Z0 TE, I'll call it 10, times tangent of beta L, I'll get to this in a second, over, and then it's gonna be Z0 TE 10 plus JZL, right, times tangent of beta L. Do y'all remember this formula, guys? That's the input impedance on a transmission line. Normally it's just Z0, but we've got to use Z0 TE because it has to be the impedance of the mode you're operating in. And we only want to operate it in 1.0 mode for a rectangular guide. Got it, everyone? So now we have to look at this quantity, beta L. Well, beta is 2 pi, and it's divided by lambda in the guide. Put that down. That's lambda in the guide. And then you want to put L, and we multiply it by L, in terms of lambda in the guide. Does everybody follow me? So I want something here times lambda, so the lambdas in the guide will cancel. All right. So now we have to find out what lambda in the guide is. Do you remember the lambda along the length of the guide? Do you remember how to get that? I bet you do. It's always going to be what? Lambda in the guide will be longer or equal to, at very high frequency, the free space lambda. Do you remember? Because that cutoff, the lambda in the guide goes to infinity, right? So that's going to be lambda free space over the square root of 1 minus FC over F squared. And in my case, lambda free space is C over F, right? And what was that? C over, it was what, 5 centimeters, was it? Class? 5 centimeters, right? 5 times 10 to the minus 2, right? Because if this is a half wavelength, if A is a half wavelength, then 2A is lambda naught, and A was 2.5 centimeters. And it's divided by this, and what is this going to be? It's the square root of, technically it's 1 minus what? 6 over 10 squared, correct, class? And what do you get for this?
Is that 5 times 10 to the minus 2?
Yeah, it's 5 centimeters. It's got to be in meters.
116.063.
0.063. So it's really 6.3 centimeters, right? Is that right? All right, now our our length is 8 centimeters. So in terms of fractions of wavelength, how long is the guide in wavelengths from here to here? Class? What is this length in lambda? Well, we take 8 centimeters and divide it by 6.3 centimeters. What do you get? I've got a few things to show you.
0.4.
What is that? 8 divided by
1.3.
What?
1.3.
That's right. This is 1.3 lambda in the guide. Because lambda in the guide was equal to 6.3, right? Isn't that right, class? Now, hear me now. So now, we want to get our beta L term. Now, I don't know if you remember this, but I hope you do. Remember, every time you move down half a wavelength, you're basically at the last point. Do you remember that? Every half wavelength, the thing repeats itself. You'll notice I'm at 1.3 lambda. So really the guide looks like, the actual electrical length of the guide is 0.3 lambda, right? That's the electrical length, because I can subtract off half a wavelength and another half a full wavelength, and I'm left with 0.3, and that is between 0 and half a wavelength. Does everybody see what I'm doing here? Do you? If you have a question, ask it. Remember, anytime if you have something that's 3.2 wavelengths long, you can forget the 3 wavelengths, because that just is cyclical. Every half wavelength, the voltage, standing wave ratio, and the voltage pattern repeats itself, right? So you can ignore that because this is lossless. Does everybody get that? So now my guide length is really 0.3 lambda. Now I can calculate this right here. This is 0.3 lambda. You could put in, if you wanted, you could put in 1.3, but it's unnecessary. Understand, class? You would not get a wrong answer. So now the lambda and the guides cancel. And I have this equal to 2 pi times 0.3. And can you give me that answer?
One point, 9.
That's 1.9 radians, by the way. Now use this for beta L, put it in here and here, and then you've got ZL, right? ZL is 400 ohms, and you've got Z naught TE, that's 471, correct, class? And by the way, this is the calculation that my other classes I'm teaching messes up left and right on quizzes. Even though they have the exact equation, they probably have it programmed in their calculator. Somehow this thing messes them up. Mainly because they don't go radians to degrees, and not only that, this J term sometimes messes them up.
Bless you.
Remember, that's J, bless you. So what did you get for this Z in here? We'll make RS 100 ohms. We're gonna go through this whole calculation. Do y'all remember doing this in calculators before? I mean, waveguides, transmission lines, right? If you had Dr. Wentworth, I know he does a good job with this. I'm sure Dr. Riggs does too.
I got 533.1 minus J 53.5.
All right, 533, save that, 0.1, minus J, what was it?
53.5.
53.5 ohms. Anybody else?
Yep. What I got.
Who else got that? You got it, you got it? I'm gonna tell you, this is the calculation people mess up, so it's smart to do this in class several times. Make sure you don't mess this up, you'll be asked about it. Now, if I have that as my Zn, right here, now I want you to follow me. I'm gonna have to erase some of this, so let's go with this. And I know this can be challenging, this right here. But this is not in Dr. Wentworth's book. He doesn't go through this. I want you, please remember that number. All right, now when we're doing this, if we want to get this voltage right here, I'm going to call it V prime. That's just on the inside of that waveguide. It would be just like the voltage V prime on the inside of a transmission line. You remember how to do this? Now I can say that my V prime there would actually be my V generator, and call V generator equal to 10 volts, just 10 volts. I can say that my V prime would be 10, right? And then it's like voltage division. This looks like just the input impedance right here. So then I put Z in, which I knew from before, over Z in plus RS, or RS. And what I can do now, I mean, you've got Z in, don't you, class? Z in was at 530 plus or minus J 53 or whatever. And you've got RS as 100 ohms. So now you can take what, you can find out what V prime is. And I know you can do this, okay? And you can give me V prime. If you don't mind, give it to me in magnitude and angle. And I'm going to warn you, do these calculations now in class, because you're going to see if you're making mistakes. Notice how you're making mistakes now, not during the quiz. Anybody? Magnitude and angle.
I got 0.14 at an angle of negative 39.
Degrees?
Yes, sir.
Anybody else? It's going to be less than 10. Well, I take it back. I got 10 times Z, and Z is about 500 and something, right? Z is 500 minus J 53. Is that what it is? 500 and something. What was Z in again, guys?
I did.
It's 553.1.
553.1 minus J what?
53.5.
53.5, alright, that's ZN.
I'm getting,
R,
I'm getting 8.43.
That sounds better.
Yeah, I did mine wrong, I'm
At
sorry.
an angle at negative 0.02 degrees.
8.4, did you say?
8.43.
Yeah.
At an angle of minus what?
0.016.
0.016. Minus 0.016 degrees?
No, that's in radians.
Radians, okay.
Radians.
Oh, yeah, okay.
It's negative 0.9 degrees.
0.9 degrees, just about 1 degree. Minus 1 degree. That's just about strict real. Now, how many remember this? This V prime is really what the voltage is at this end, but it's based on the superposition of a forward traveling and a reverse traveling wave. Do you all remember? So my V prime here is actually equal to V0 plus times E, normally it's E to the minus, let me just tell you this, the normal equation for a voltage on a transmission line is V of Z is equal to V0 plus times E to the minus J, this is lossless beta Z, plus the reflection coefficient times E to the plus J beta Z, right? But something I didn't tell you, consistent with Dr. Wentworth's book, the load is always assumed at Z equals 0. So this point right here is actually Z equals minus L. Y'all remember that class? The transmission line, they always put the load at 0 for transmission line problems, and that means the input has a negative value of Z, which means that this equation over there, with a negative value of Z, with a negative value, sorry, when Z becomes minus L, this becomes plus J beta L, so it's E to the J plus beta L, and then it's going to be plus the reflection coefficient times E to the minus J beta L. Now, beta L is something that I erased, but we had over here, remember? It was, I don't remember, 1.9 radians, right?
Yeah.
So now, I want V0 plus, this is my point. So what I'm going to do is say that V0 plus, we're almost done, is going to be 8.43, and it's going to be E to the, or really at an angle, let's put it at an angle, of minus 0.9 degrees, and then that is divided by this quantity, E to the J beta L, plus the reflection coefficient, and I hope you have that down, reflection because I erased it, reflection for coefficient E to the minus J beta L. I'm going to tell you right now, lots of different answers for this occurred, but this is important you get it right. Remember what gamma L is? Beta L is 1.9, and there is a polarity difference. This is a minus J beta L, and that's 8.43 at an angle of minus 0.9 degrees, not radians. See, this problem makes a lot more tangible sense than just checking the mode values for and stuff like this. This is a real world problem, given.
What gamma L?
What? Reflection coefficient?
0.08.
Isn't reflection coefficient minus?
Yeah,
Minus
-0.082.
Minus 0.082? Let me just put that in there. Reflection coefficient is minus 0.082. I know it seems trivial to do this, but it's important. You can't do what?
This, I have another calculator, this one won't do like E to the J's.
You do have a calculator.
I have a
Bill.
calculator that does.
Make
but
sure you bring
I don't
Friday.
have it with me.
Okay, bring it Friday.
Yeah. I forgot this one that do that. Beta's 1.9 right now.
beta L,
Yeah,
beta times L. Did I mention MathCAD in here? No. I use MathCAD, it's the free, I have a free, you can get it for free, and MathCAD, maybe I should show this to you, and I will in a little bit. I can do these calculations like that, so what you see is what you get. It's not like running MATLAB where you have to rerun the script all the time. I change one variable, everything changes automatically, and I like it for stuff like this. It doesn't have the horsepower MATLAB does in terms of matrix calculations and doing pretty extensive programming, but it's great for these type of problems, lower level problems. Anybody? This is a nasty little calculation, these couple.
Okay, the domain error.
Yeah, that's another one you I expect to see.
What am I again?
You remember you got radians and degrees.
Degrees.
Is 4.94 volts, -93 degrees?
It's possible. 4.93.
Hey,
4.93, what?
4.94 at
Four.
-93 degrees.
4 at -9, what?
3?
0.3?
No,
9
it's
point?
93.
90. Minus 90 degrees?
Yeah, minus 93.
93.
Yeah.
Minus 93 degrees. So it's about minus J.
Yeah.
All right, I don't know. Can anybody second? I'm prepping you for what you're going to get on Friday. Anybody? Nothing. Nothing to get it. That's right. Since we're experiencing so much technical difficulty, what I'm going to do is actually take time, open up. Maybe I'll show you this little gem of mine. Now you can get and I've worked with the version that is not free, that has everything, and it's really nice for doing these kind of problems. Now Dr. Wentworth and a lot of people say you should do them in MATLAB, and I'm not saying he's wrong, but this is a lot easier. And as an engineer, I go for easy. This is always kind of a mess. For me to cast something, it's oops. Or I can't Chromecast there, I don't think. So I wish I could. You know what Chromecast is, guys? Chromecast is something, it's a device you plug into the USB of your TV, and then you can cast right from your computer. It's great.
Yes.
So my second calculation is 7.91.
That's what I'm getting.
And -107 degrees.
All right. Well, thank you. I'm going to try to help you guys. But I'm going to show you the way I do this, because I think you'll appreciate the benefit of using what I'm going to show you. I'm going to come down here, and
What was that number that you got?
-107.
You want that projector to come down?
huh? Yeah, I'll get it down. I'm going to just do this. See this? I got enough time to do something like this at a relaxed pace in this class, because we're on schedule here. Now I need this cord. Hmm?
I got that, but I have some gradients.
I'll just show you what I'm talking about. I think you'll understand why I like this. In fact, let me take it all the way down here. I give you a frequency of 10 gigahertz, right? Operational frequency. And cutoff was 6. Oh, sorry. This is 10 to the 10th. Is it showing? Okay. Here's what I'm doing. I'm just putting in the values for cutoff and stuff like this. I can enlarge this a little too. All right, now I normally cause, if I have if something that's going to reappear over and over in a calculation, I just cause I call something K. And K is going to be equal to the square root of 1 minus the quantity FC over F squared. Just watch this. Are you with me? So that means K is that. It's 0.8. Then after that, now I'm going to go ahead and remember what we're after. My Z, all right, I'm going to say A to naught was equal to 120 times pi, right? And then I'm going to say the actual Z, I'll call it just Z naught. Come on. Call it Z naught was equal to A to naught divided by K, correct, class? Are you with me? So let me see what I get for Z naught. I get that. Then after that, now I need Zn, right? Correct, guys? So Zn was equal to Z naught times the quantity ZL, and I got to put ZL in there, plus 1J times Z naught. Come on. Z naught times tangent of beta L, and I'll leave it as just tangent beta L. And then I have to take that and divide the whole thing by Z naught plus 1J times ZL times tangent of beta L. And after that, I found out that beta L, well, I found out, I can do this, lengthen the guide. I found it first that, I'll just call it lambda, LAM. Actually, this is unguided was C over F, right? C over F, and I hope, and that means lam unguided was 0.03, right? Is that right, class? And that means lambda guided, I'll just call it lam in the guide, was equal to LAM, right? Come on, divided by K. Are you with me? Because I just get that constant K, so I don't have to keep that square root up again all the time. Now after that, so I get lambda in the guide. Equal to that. I'm going to take this and move it down a little bit. Sorry. And then I'm going to actually scroll this whole thing down. So then after that, I have beta in the guide is equal to well, it's beta in the guide, actually beta in the guide times L in the guide, so it's 2 pi over lambda guide times the length in of the guide in lambda and L. What was the total length again? Was it 8 centimeters? 0.08, so that means L in the guide, the length is equal to capital L divided by actually lambda in the guide, right? And that means L in the guide is equal to that. Wait a second.
The total length of the guide was 6.3 centimeters.
I thought it was 8.
The wavelength of the guide
The wavelength.
was
6.3.
Oh.
Wait. did you get lambda? I got C over F for lambda is 0.3 centimeters, is that right?
Lambda?
Oh, you know what? I think I know where the problem is. That's right.
It's 0.3 instead of 0.03.
Well, isn't the frequency 10 gigahertz?
Right.
So 10 gigahertz. Can you start that thing? Just hold on for a second. The frequency's 10 gig, right?
You're right.
All right, that means that lambda unguided is C over F. 3 times 10 to the 8th over 10 to the 10th is 0.03. It's 3 centimeters, right?
We took into account, the A value.
Ace, that's the cutoff frequency. This is the real lambda. Remember, our cutoff frequency comes from that, the A. This is the actual, maybe there was a mistake made. The actual lambda is C over F, unguided, right? And then if you want lambda in the guide, you take C over F and divide it by K. Maybe I said something wrong. That value of A has to do with the cutoff frequency, not the frequency we're at. Because we're at 10 gigahertz. The cutoff frequency is at 6 gig, right? Right? If it was 6 gig, then it would be much longer. So this means the actual unguided wavelength is 3 centimeters. In the guide, it's 0.038, correct? Isn't that right? Just take lambda divided by K, and K is 0.1, isn't it? Can you turn that thing off?
Yeah, I'm waiting on it to count down.
Do y'all follow me on what I'm saying, class?
Where does K come from?
K is the square root of 1 plus FC over F squared. The reason I made K is because the 1 over the square root of 1 minus FC over F squared keeps reappearing, so I called the constant
Okay.
K. It makes it easy, doesn't it, class? You'll see this in a second. I hope you download MathCAD and play with it because it is phenomenal. And there are a few tricks. You don't just put an equal sign, you have to put the semicolon the colon is the equal sign here if I'm setting something equal to something. But if I'm looking for the value of an equation, then I hit the equal sign. And there's just a few little things. It's gonna be laptop, that's right.
Well,
You're okay.
Projector's all, let's see.
Down here. Projector, hit that. On. All right, it's coming on. It'll come on. Takes a second to warm up. Just leave it like that. All right, now that I have this lambda in the guide, and beta is, now I can say this. You can't see what I'm doing. That's going to be, just hang on, times pi, times, and then it's going to be length of the guide, L, divided by, and that means beta L. Wow, beta L is much different than what we had. I must have led you astray somehow. I think we used the wrong value of wavelength.
I think, because for K, the K is 1 over square root or just square root of 1?
No, I just used square root of 1 minus,
FC over F squared.
it's not up yet.
Yeah.
Is that coming on?
I got 0.8 for that.
For what?
For K.
Yeah,
0.8?
no, it's 0.8, isn't it?
Yeah, I got 0.8. Okay, I didn't know.
Oh, 0.8, yeah, I'm sorry.
Yeah, I can't tell if that's what you have.
Hold on. No, wait, just leave it.
That did it, I think.
Is it on?
It turned green. It
All
was
right,
on.
it'll be on in a second then.
Okay.
It has to warm up.
Wait, so once you have a K, are you trying to find the wavelength in the guide since you know K?
Yeah, the thing is, I know the wavelength's gonna be longer, so I divide the actual wavelength, lambda 0, which is C over F, by K. And
Oh, okay, yeah.
Oh, I
C
think-
over F.
I think I know.
We use 5
We were
centimeters
doing-
for C over F?
Hmm?
5 centimeters for C over F?
No, C over F, F is 10 times 10, right? C is gonna be 3 times 10 to the 8th over 10 to the 10th, right?
Yeah, we weren't doing that.
We used the wrong frequency, that's my bad. I gave you the cutoff frequency.
So
It should be the frequency of operation, which is 10.
10 gigs.
So we have the wrong lambda knot.
No, we don't, though. We got the right lambda knot, don't we? Here, I call, this is lambda naught, this is free space right here.
You have it right.
Yes.
We have it wrong.
Yeah, we originally.
You were led astray by
we
the
all
false
originally
prophet
wrote
of
down
electromagnetic.
5 centimeters.
Yes,
Yeah.
stone that false prophet. All right, you got it right now?
Okay.
Now, so that means lambda in the guide is that lambda over k, right? And I got 0.038, right? Now I need to know the length of the guide in wavelengths in the guide. So I take L by lambda over the guide, right? And then I multiply by 2 pi. Because remember, beta is 2 pi over lambda, right? That's lambda in the guide, times L. L is the length of the guide in lambda. So it's 2 pi times L over lambda in the guide. Understand, everybody? We could have done it beta unguided times K times the actual length. And matter of fact, I'll do this. So beta unguided right here would be what? Well, beta unguided would be omega squared divided by C. I'm not gonna go that route. We could play this game a lot of ways, but you know, beta is omega square root of mu epsilon. Square root of mu epsilon is 1 over C, so it's omega over C. And then if it would be beta squared, it'd be omega squared over C, or omega squared over C squared, right? I don't mean to. All right, just work with me here. Are we all together on this, guys? Do you get beta L to be that? That's radians too.
I got. You got
It's beta is 2 pi over lambda in the guide times the length of the guide in terms of wavelengths, right? And that's wavelengths in the guide, so it's L divided by lambda guide, right?
I got 13.2.
I got 13.4. I mean, you're using a calculator probably with a lower resolution. You probably have
Yeah,
a,
it's pretty close.
it's close, all right. Do you all agree with this now? Do you see it? You're looking at me like you don't believe it. Are you okay with that or not?
Yeah, I think so.
All right, now this is the Z. I got to give you, where's my ZL? Did I put that? No. I need to put ZL, how about right there? ZL is actually equal to, I made it 400, didn't I? Right? Come on.
ZL, yeah.
All right,
ZL
now,
400.
this is the ZN I get now. It's gonna be different. I got 473 point something plus J77. Yeah,
Let's see, earlier we did, we did L over lambda guide and got some answer.
it's right here. Look, look, look.
But we had that.
L over lambda guide. You want me to do it right here? Break it
Yeah,
out?
like, I'm just saying earlier we got like 1.3 for that, and you said like halfway.
Right,
length
you
and
can,
whatnot, and
you
knock
can,
it out.
right, you can do that, but this is what happens here for this one. That's 2.133, because
Yeah,
we're
so
using
then
it.
Could we just use 0.133?
That's right.
Okay, that's.
Point
that-
one
that's-
three three.
Huh?
It's a repeating thing. It's 0.1333333 probably.
Yeah. So that's why I was confused for a second, because I just used 0.133.
That's fine.
3 times 2 pi.
That's right.
And
That'll
got
do
me
it
the
too.
L value.
Can you show where the L is coming from?
L is right here, right? And that L is defined right here, 0.08. That's something I stated explicitly as the length. We didn't calculate it. It was given. Are you with me?
Okay.
Guys, everybody? You'll like, this tool's kind of easy to use too. All right, now after I got Z in, now I've got to get my V prime, right? I'm going to make a few more points. V naught, or V source here, was equal to 10. Didn't I say it was 10 on the board, guys?
Yeah.
VS was 10. RL, or I mean R source was 100. Didn't I say that? So now I can get V prime, and that means V prime, I'll just call it VP, was equal to VS, right, times ZN, divided by quantity ZN plus RS. Agreed, everyone?
Yes, sir.
That's voltage division, and that means my V prime equals that, and if I want the magnitude, I can just do, this is great with this one. Now, if you get the full version, I can tell you, you can go from Cartesian to polar. Anyway, you can do all that stuff on the fly in an instant, but I don't have the full version. Okay? Everybody catch up. make sure you see where I'm at. Now I've got the voltage just inside the waveguide at the towards the source end, right? Everybody with me? Now what do we need next? We need V0, right? Remember that equation? V0 times e to the j beta. All right, so now when I get V0, work with me here. My V0 is going to be that V prime, VP, and it's divided by, and this is one where you got domain errors. So I don't know what kind of domain, I don't know what the problem is, but I have a feeling.
I figured it out.
Huh?
I had it in
Radians?
mode.
There's weird things that happen when you do these things. So now I have to divide that by EXP. I'm going to put EXP, I don't have to. And I've got to put 1J there. You always have to put a 1 in front of the J when you do these, just like with MATLAB. Then it's times beta L, right? It's that plus, and then it's the reflection coefficient. Where is my, did I put that down? I don't think I put.
Mine is 0.08.
Yeah, but I'm going to go ahead and put it down. I just put, I'll put gamma small l here, equals, and that's going to be ZL minus Z naught, right, over ZL plus Z naught. And my reflection coefficient that I get is that minus 0.082. Agree, class?
Yep.
So now I'm going to go ahead and say it's that reflection coefficient, which is gamma L, then it's times, and this is EXP put to the minus 1J times beta L, right? And that gives me a V0 of 25 plus J43. Is that what you guys got? Punch in the calculators, because remember V prime was right here, right? When I divide it by that, that's what I get. Did you guys get that? As a matter of fact, I'll give you the magnitude of V0. I'll tell you a lot of calculation errors. It's 50. It's half the actual source voltage, which is interesting. I didn't do this by design, by the way. It's a coincidence. Did you get it? You know, if you could see what I see, I see people here that are just whipped.
It's just so easy to get lost in this little screen.
I'm going to tell you something. That's why I write these things down, the calculations, and anytime I have something complicated like tangent of beta L, I'll call it A or something. Store that value. Don't keep on redoing calculations. Do it one time, store it, and then recall it. But you're right, it is easy on these calculators. Is yours a TI?
89, yes sir.
Well, that's pretty good graphically. Doesn't it have some good illustrations there?
Yeah, it's just, I don't know.
One of the dangers is you try to do it all at once instead of writing down intermediate values and using them.
So what'd you get for the magnitude for?
50 for V naught.
Okay.
Can anybody else confirm what's showing on the screen here?
I can confirm that magnitude, but I can't confirm the V9s. I can't get my calculator to calculate it.
So-
Wait a second, V
I
naught.
just converted the V9 in rectangular to over and got that magnitude.
Well, that's it. Your V naught in rectangular was 25 plus J43, wasn't it?
Yes, sir.
All right, well, you got it. Didn't you?
I'm saying my calculator, I can't calculate for V9.
The magnitude?
No, the rectangular coordinates.
Oh, wait a second. Wait. Hold it. This is V's. I have small zero here. Where did I call? What is? Oh, sorry. This is V0 here. Sorry. There we go. Is that what you guys got?
Changed it.
8 point. Yeah,
Yes,
sure.
that's what I got.
I'm
8
sorry.
point.
I have calculations above that. My bad, guys. And you see that small, the 0 versus the O. This is the numerical 0. The one that was there before was small o on my tablet. Sorry, I'm sorry about that. Did you get this?
Is it
Like I said, I'm not able to calculate that at the moment, the V0.
Did you get VP?
Yes, I got that, but I'm not.
What is this? Giving you a domain error?
That's what I'm getting.
He had that too. He said it was due to radians, degrees things.
Did you get an angle for V?
I can get it for you if you want me to. You want the angle? But did you get this in rectangular right here?
I've got mine set,
Well,
polar.
I'm gonna bet, did you get that
Yeah,
magnitude?
it's-
Did you get
I got
8.195?
8.197.
Then I'm gonna tell you, it's gotta be the right answer. Because the phase angle on this one, this is one of those things, it has to be one and the other.
Okay.
If the magnitude's wrong, the phase angle is wrong. If the magnitude's right, almost guaranteed the phase angle's right. Almost guaranteed. All right, now, next, the whole point was finding the voltage at the load, right? So what would the voltage at the load be? Do you remember?
Yeah.
Guys, if I have the reflection coefficient and I have, look up there for a second. Matter of fact, let me do it. That way I won't have to run back and forth. I don't like working down here, but I will today.
Because this is for this magnitude and an angle and specify
Let me see
it's
if
in
this
degrees.
works.
You should be
Tell me if, that's a docking camera, is it?
fine. Okay. You should be able to do it if you. Radians. Yeah, try that. So now, that's the wrong answer, but that's what we got earlier.
Is that not the?
But the
No,
magnitude is
there's no
correct,
signal for
that's
this?
in radians, so you're gonna have to convert that to decimal. So it'd be 1.8697, then converting from radians to decimals just times 180 over 5. So it's really negative 107 degrees.
How come there's no signal from the docking cam now?
So the correct answer we just got for that one. Yeah, I got the right magnitude, just the angles in radians. So I had to convert it to negative 51. It's very confusing.
I don't know why the document cam doesn't work now.
Did you pull that HDMI you ran to your laptop? Was it in the document?
Mm-mm. Was this document cam working before?
I don't know.
I know Geiger uses it in the class before.
All right, guys, I'm gonna level with you. I don't. All right, just go with me on this one. You see that equation right there? All right, that's generally true anywhere on the transmission line. We just, or the waveguide, we just calculated V0 plus, right? So if we want the voltage at the load, then the only thing we have to do is let Z equal 0. Does everybody see that? If Z equals 0, then I have the voltage at the actual load is going to be just V0 plus. So it's going to be my V0. Come on. This thing keeps popping up. It's going to be my V0 right here. Then it's going to be times 1 plus, and it's just going to be gamma L. Follow me on that? Everybody? Because beta Z now is 0, right? I'm at the load, and therefore my voltage at the load will be equal to that. Now, could you tell me if you get that? If you got V0 right, it's got to be right. Or a magnitude of this. Is that what you got for magnitude of voltage at the load? It's 1 plus the reflection coefficient times V0.
The 1 plus. should be
Oh,
in
wait a
parentheses,
second.
Right?
Oh, yeah, my bad. Yeah, sorry. Thank
Okay,
you.
yeah, that's what I got.
You guys get it?
So 1 plus the reflection times your V0.
many have 89s in here?
7.5.
You got an 89? Are you having trouble too with domain error or something?
It's just the converting from radians and degrees. It's confusing. If you have it in radians, it works fine, but you just have to convert it back to degrees.
I would say this, if I was you when I'm doing these calculations, just a piece of advice, work all in radians. All right, I'm gonna just suggest it. I'm not gonna convert everything to radians so you eliminate the possibility of these domain error problems.
Or
Yeah.
if you put everything in rectangular, it'll prevent it from doing the domain error stuff.
But e to the
Yeah.
j beta is L. I guess if you put it in, can you put in e to the power j?
You can put
Yeah,
it
that's
that
what
way.
I've been
Okay.
doing.
All right.
On the 84, you said one above pi over the 80 period.
Yeah, 7.5 to
Pi over 180 takes degrees to
The
radians.
84 only takes e to the
J in radians.
in radians.
You can't
Oh.
do e to the j in.
Is that what you have in 84?
Yeah.
So I have to multiply by pi over 180.
All right. You know, I'm going to confess to you, I don't have an I have an HP. I have a very old HP that does everything, but it has what's called reverse Polish notation. So all the calculations are done like a stack register. It's first in, last out. And if I wanted to do a calculation of 1 plus 3 times 2, I would plug in 1, plug in 2, then plus, then I would have equal, right? Then times 2. Follow me on this? In other words, you do everything as if, you know what a stack register is? First in, last out, right? So you do your mathematical operations on the first thing you enter, like you put the first two things, then 1, instead of 1 plus 1, it's 1, and then say 2, 1 plus 2, and then plus. So now those two things you're going to add. That value you want to multiply, then you put times something. And you don't have, like yours, you literally see it on your screen, right? 1 plus 1, and you have to put an equal sign if you want a value, don't you? I don't in mine. But that's what I grew up on, so I like it. And it's old. But I think TI now is the most favored calculator for engineers. I think. But I'm saying that because I don't know what Civil uses. All right, after I did this problem for a reason. This is a real application of a waveguide with the communicating power. Dr. Wentworth's book has nothing about this. He only calculates mode values, phase velocity. By the way, if we were going to get the phase velocity, we might as well do this whole thing. If we wanted the phase velocity on that, since it is air-filled, what would the phase velocity be? First, is it greater than or less than the speed of light?
Greater than.
It's greater than, right? It's going to be c divided by k, isn't it, class? So my phase velocity is going to be what? 3.75 times 10 to the 8th. Everybody with me on this? But what is the actual group velocity or the velocity of energy? I'll call it VE. That's equal to what? It's actually equal to c times k. So it's going to be 80% of the speed of light, or the velocity of energy. You all see what I'm doing here?
Yeah.
Energy is less by how much? By k. Phase velocity is greater by how much? By 1 over k. Then the speed of, really the speed of electromagnetic energy in an unbounded region. So if it wasn't air, if it was something that had a phase velocity of like 2 times, or a velocity in the unbounded media of 2 times 10 to the 8th, then you would use 2 times 10 to the 8th. All right, now that's, so that's phase velocity, right? We got wavelength in the guide. You got the impedance of the guide. We pretty much did everything about guides, right? We got the cutoff frequency. We could get, the second cutoff frequency would be a 12, and then the next cutoff frequency is the 1-1 mode, or the 0-1 mode, pardon me, 0-1 mode. And we could keep messing around with that, but it's not worth it. This is a little better problem in terms of an application of a waveguide, more so than just an analysis of abstract fields. Okay? Remember, MathCAD. I'm not getting paid to do this, but I give them a thumbs up because I can do problems on MathCAD, and believe me, I'm used to doing them so much faster than on a calculator or on MATLAB, if they're relatively trivial problems, not not, MATLAB does great root solving, it pivots matrices, it has all sorts of powerful toolboxes. But in terms of what you see is what you get, and change one variable. For instance, I'm making a quiz up, I'll just do this, but now I'll change it from 10 gigahertz, all right, operating at 10, I'll put it at 7.45 gigahertz. All right. So now watch, bang, everything at once. And now I got a new quiz. And I can change the length, if I want to change the length L from 0.08 to make it 0.05, bang, at that frequency. And it's real nice for professors to create quizzes by modifying homeworks. And this is what I do all the time. Anybody that has anybody had me in here? You have. Anybody else? You have. You have. Nobody? You have, haven't you? Haven't you had me before? No? All right, well, if you have had me before, you know my homeworks and quizzes are virtual. They're basically modifications of homework. I give a lot of homework and I just modify it a little. So if you know how to do the homework, the quiz is an automatic. But if you don't know or cramming, then you won't know usually how to do the quiz. You'll be fumbling around, okay? And I try to be very fair about all this. Does this example seem okay? You all see how this is an application of a waveguide. All right, the next thing I'm going to do is actually going to be the dielectric waveguide and then fiber optic guide. Since that isn't working, I got to hop back up to the board. Thanks for bearing with me. It's a little foolishness. Now, let me say this about these slab waveguides. I'm trying to come up with problems that are more applicable, like the ones we just did. But slab waveguides, what we're going to talk about with the slab waveguide, it is something that is used on chip a lot of times over a short distance just to communicate optical information from one part to another. Now, the real way outside of the on-chip stuff it's done, you don't have a long slab waveguide as far as I know. That's something that's very small distances. Whenever you get outside of a chip operation, you want to run this to Haley set or something, then you have fiber optic cable. And then you have optical repeaters and things like this. And I'm just going to level with you. I am not an expert in fiber optics. I've never actually spliced fiber optic line or done anything like that. But I know about the signaling, and I know a lot about how it works. But I've never been in a technical position to actually take a piece of fiber optic and do any kind of real connections and stuff like this. Now I know it's not hard to do, but the old, real fibers. Fiber optic stuff is silicon dioxide. It's glass, right? And when you get a cut in one of them, you have to fuse it together. You literally have to weld the thing, basically remelt the thing. It's a lot of tricks like that. I've never done that. So I'm going to keep my comments to what I know about. And if you're in the real world, by the way, as an engineer, I'll tell you this. In a lot of cases, you'll never ever see the final product that you're designing portions of. That final product is assembled somewhere else or fabricated somewhere else. When my wife worked for Intel, she did all sorts of testing and verification. When they found a problem or a flaw in the chip's operation, they did corrective measures, but the real fabricated product was done somewhere else. They call them foundries, where they actually do VLSI stuff, very large scale integration, they mask it. She was never around that. So, I'll tell you, as engineers, you may be a long way from where your product that you're working on is actually created, the final product, but you're gonna be involved in it at various levels. So, here we're gonna do, this is the slab waveguide, and then we'll do fiber. So for the slab waveguide, first thing we're going to do is talk about the critical angle of operation. And again, when we have a slab, we basically have this. Guys, call this N1, and this is really going to be the square root of epsilon relative 1 in the guide. So this is the guide. And then out here we have A to 2. Now, unless there's an obvious reason to use something else, A to 2 is just airs, and the square root of epsilon relative of air is 1. So I'm assuming this is air because that's almost always what it is. And A to 2 here is air as well. Alright? Now, what happens in a guide, there's a thickness of the guide. It's D. A slab waveguides really look like this. They're very flat, thin things like this, and this is the dimension you care about, A. And this dimension is like 50 A. It's much, much larger. You care about the short dimension A, right? That's the one you worry about. Now, when they actually do these problems, they cut it right down the middle, and this is the 0 point. So this is A over 2 down, A over 2 up. And when they get the electric fields, they're going to have them as functions of position. This is usually called X, and this is usually called Z, or at least in Dr. Wentworth's book. Now keep that in mind, and let me show you what the first calculation is that you have to understand about these guides. And we can have both TE and TMOs, just so you know. Both exist in this. The first thing we do is calculate the critical angle. Let me extend this guy a little. So what we do is this. If this is, remember, this is something with an epsilon relative of 1 greater than 1, make sure you put this greater than 1. We use Snell's law in here, and we say that here's what we're after. We know that we have some theta incident here, theta transmitted here, right? And this is the direction. There's the interface. Now please watch this. We use Snell's law. Snell's law says beta in region 1 times the sine of the angle in region 1 is beta in region 2 times the angle, in this case transmitted, or in region 2. Beta in region 1 is omega times square root of mu 1 epsilon 1 times the sine of theta incident is beta in region 2, and that's omega times square root of mu 1 epsilon 2, mu 2, pardon me, epsilon 2 in region 2, and this is times the sine of theta transmitted times the sine of theta transmitted. Now, are you all with me on that? This is just Snell's law, right? Now, you'll notice that omega goes away, right? Next, you'll notice that since it's non-magnetic, and we'll assume non-magnetic, this is non-magnetic, then we get this. Now, this is the one thing I'm going to mention. Remember, the index of refraction is symbolized by the letter N, and it's the square root of epsilon relative in that region. Correct, class? Now you can use eta. I prefer to use, N1. I prefer to use epsilon relative because that's something that's sticking with you, right? Sometimes that N looks like an eta, looks like an intrinsic impedance, and Dr. Wentworth's book has a mistake in it about that. But if I look at this right here, I want to find out the angle. I'm after this angle, so that it will be the critical angle. And here's what I mean by that. I want to find this angle so that any angle greater than that angle will cause complete internal reflection. I want everything reflected. This is the critical angle, isn't it, class? When everything is internally reflected. Now listen to me on this one. Since I said region 2 is air, this is just 1, isn't it? With me? And if that's just 1, well, if it's all reflected, that means this transmitted angle goes to 90 degrees. Do you follow me on this? That's the trick on this one. What's the sine of 90? 90 degrees, pardon me? 1, right? So that means then this equation simply becomes the sine of the critical angle, or the incident angle, becomes 1, because this will be 1, over the square root of epsilon relative in region 1, or in the core, in the white waveguide. And therefore the critical angle is equal to 1, is really equal to the inverse sine minus 1 of 1 over the square root of epsilon relative 1. That's the critical angle, understand? All our operations in the waveguide have to be at angles greater than the critical angle. It means when you feed energy into here, right, it has to bounce at this angle has to be the critical angle or greater. Follow me on this, class? Are you with me? Now this tells me a lot about how I'm gonna feed it in. I'll get to that in a second. Next, after that, we'd have to go through a little analysis that I'll do over here. And this is laid out in your book. Remember I had that drawing where I had a waveguide, and I'll try to blow it up here. This is a slab guide. This is dimension A, right? And then what I showed a wave coming in here and striking, and has a reflection coefficient of this surface, then penetrating down this way, right? And striking, and then coming up this way. And this angle right here would be this angle, and this would be the incident angle. But this angle here would be 2 times the incident angle. And furthermore, I said that I want to get an equal phase surface, so if I take the actual angle it's striking here and I draw a perpendicular here, and I say that really I want, if you think about this, I want the thing to hit, come down, hit, and I want this point and this point to be at the same phase. Do you follow me on that, class? This is how his book discusses it. Just think about this. I want an equal phase surface bouncing this way, so that means when the signal hits here, it comes down, hits here, and then bounces up. This has to be the same phase, or 2 pi times n times the same phase as the point here, or else it'll be out of phase and it'll be destructive interference. Can y'all envision this? Please watch me on this one. So he labels this point A and this point B in his book, and this point he calls C. Now try to understand something. There's a reflection coefficient here that's actually got a magnitude of that reflection coefficient, and there's some phase. Here, there's also a reflection coefficient and there's some phase. They're assumed to be the same thing. In other words, when you're talking about a slab waveguide, it's usually air outside of it. Just air. It's not like you don't have metal on one side and air on the other, all right? Now, in his book, what he has is this. He says the electric field coming incident here has a value of E naught. Now, when it hits here and reflects, now he says it's going to have a value of E naught times gamma, or really times magnitude of gamma times e to the j phi. Does that make sense to everybody? Right? It hits, it's just the incident field, whatever it hits with, it was E naught. I'm calling it E naught. I think he calls it EA. Right? Then it scatters with gamma, the reflection coefficient, times that. Now listen, as it's propagating down this way, right, it undergoes a phase shift to this point. Right before it hits, the field value right before it hits would be this field value, E naught, right, times gamma times e to the j phi, but now it goes through a phase change, e to the minus j beta times, and this would be the length of small ab. Here's A, here's B, it would be that length that went through, right? So there's a phase change, and since it's propagating, it's e to the minus j beta, that would be beta in the unguided region, times L, AB, all right? Are you with me on this? Now it hits here. Now there's another phase change, right? It's going to be gamma again times e to the j phi. So now, right here at this point, just on the other side of it, the field's value here is going to be E naught times magnitude of gamma. Now it's gamma squared times e to the j 2 phi, because now we've got that multiplying it again, so it's e to the j 2 times the phase angle, and then it's going to be times e to the minus j beta LAB. Just hold it right there. But notice what happens. To get to this equal phase surface, it now goes through B to C, doesn't it? So I have to add that in here, plus LBC, and that's the value of the field here. Can everybody follow me there? Now something you can say, and some of you will say, well, if gamma doesn't have a magnitude of 1, it's decay, and that's altogether possible. There can be some decay, but it's still constructively adding. Do you follow me on this, everyone? Now, how is it gonna be constructively adding? And the answer is when we take all these phases right there, when we take minus beta times LAB plus LBC, and the 2 phi we'll put in front of it, they have to be equal to 0, or really they have to be equal to 2 pi m, where m is the mode number now. It has to do, that m value would have to do with the angle above the critical angle. Do you follow me? This is a little abstract and probably a little irritating. Let me finish my thought here and I'll make this up to you. All right? Now, what is LAB? Just look here. Well, anybody want to take a shot at this? What would LAB be? If this distance was A, right? This is LAB, right? Well, what is that? Isn't that it's A divided by the cosine of that angle? Because what? The cosine of this angle is what? It's this distance divided by the hypotenuse, right? So if we want the hypotenuse, we take A divided by cosine. So this is really LA, or just A divided by cosine of the incident angle. Just bear with me, I'm going to get through it. I'm not trying to rush, and I know I'm holding you, but we had technical difficulties. Now what about B to C? Take a look at this. All right, well this is what? Isn't this, boy, I'm going to try to do this right. If this is a right triangle here, right? Can you all see this? Then isn't this 2 phi, or I mean 2 phi incident right here? If I take the cosine of 2 phi times LAB, that would be BC. You may not like it, but it's true. So LBC would be equal to LAB, right? And then it's going to be times the cosine of 2 times the phase angle, 2, right? Can y'all see that, guys? Like, I'm trying to make this a right triangle right here. So this is the adjacent side, that's 2 phi. Well, cosine is what? It's this divided by hypotenuse, right? So if I want this, what do?
Hypotenuse times.
I take the hypotenuse times the cosine of 2 phi, right? Isn't that right, class? So now I get this. By the way, something to note here, and here's the last point I'm going to make. When I look at this, well, what is cosine of 2 phi? Do you remember this proof? He's got it at the bottom of the page. He says cosine of that is equal to 1/2 times cosine of 2 theta incident plus 1. Does he say that? You all see that at the bottom of that page that this proof's on? This is slab waveguide. It's got it bouncing. Anybody give me a page number on that? It's there, please. So the very bottom at the, I mean literally at the, it's a subscript.
Oh, I see it now.
What page?
401.
401. All right. Now, what I'm going to tell you is this. We have the cosine of 2 theta incident, right? So now I multiply this by 2, get rid of that, and then I subtract 1 for it. So 2 times cosine squared of theta incident minus 1 is equal to cosine of 2 theta. Just bear with me. Guess what? That goes in for here, right? And then I got LAB equal to this, right? Right? I'll tell you what, I'm holding you too long. I want you to read through this part for Friday. I'm going to go through this in fiber optics on Friday. Your quiz will be on waveguides, but it'll be a problem like the one I've done there, because that is an applicable problem. That's an application. And I'll give you a few more, okay? All right, if you have questions. Did you guys understand today with the wave, how to take a waveguide, make it look like a T-line? That's a very good application. It's not covered in the book. It's a very fair application. And I don't know why that document wasn't working. Now seriously, what I said about math test, you'd like what?
Before you erase, in the book, it has beta times length of AB plus length of BC minus 2 phi.
Here's what he's done. It doesn't matter the order. Remember,
Okay.
N could be plus or minus.
Okay.
It doesn't matter. but you're gonna find out this, here's what happens when we do this. When I take this cosine 2phi and I put it in here, and then I put A over that, the whole thing boils down to just 2A times cosine. So this has a, you're gonna have a cosine squared, it's gonna be 2A times the cosine of theta incident will be the added distance. And that makes the problem real easy.